What this means is, if you're really smart, checkers is tic-tac-toe. It's not at all complex. Checkers is only complex if you're in that interesting in-between region, if you're reasonably smart. Now, the same could someday be true with chess. Someone might write a paper saying chess is solved. What is now a complex game, chess, is really tied only to our own limitations. Once we become smart enough, it could become the equivalent of tic-tac-toe. So what have we learned? We've learned that when we say a system is complex, what we mean is that it produces interesting, non-periodic patterns and emergent structures and functionalities. So it's not a simple orbit, it's not chaos, there's structure. In this lecture, we've started to explore how varying the characteristics, the attributes of a system, make it more or less complex. And we've found that complexity tends to lie in the middle region, where we have moderate levels of interdependency, moderate levels of connectedness. We've got some diversity, but not too much. And things learn and adapt, but they're not super smart. If we adjust these dials too far to the left, nothing interesting happens. And if we adjust them too far to the right, we basically tend to get equilibrium, or for completely different reasons, we get a mangle. For example, if we have too much connectedness, every entity responds to an average, which isn't complex. Or, as we just saw, if we turn learning way up, the entities tend to produce an equilibrium. Implicit in what we've learned is an explanation of why we see so much complexity in the social world. And we'll talk about this in the next lecture as well. People are connected through networks, both spatially and geographically, but we don't interact with everyone. We also have modest degrees of interdependency. We care what other people do, but it's not the case that every time someone we know changes a behavior that we feel compelled to change as well. Nor is it the case that we're immune to changes in the behavior of friends and coworkers, right? We're in that interesting in-between. Now, we're also diverse. We're very diverse, but we're not that diverse. We eat similar foods, we pursue broadly similar goals, and we carry around roughly the same bag of tricks as everybody else. Now, finally, we're smart. We adapt, and it's that adaptation that keeps things sort of churning. But we're not that smart. It took a team of computer scientists with an enormous computer to solve checkers. Checkers! We haven't even solved chess yet. So, contrary to what economists assume, we're hardly up to the task of optimizing in all circumstances. What we do is we apply rules that we think make sense, and we adapt those rules when they fail to perform. So in sum, we're connected, we're interdependent, we're diverse, and we're smart. But we're not at the extremes on any one of these. So the worlds we construct is necessarily complex. In our next lecture, we're going to dig a little bit deeper into the other roles that diversity plays in complex systems. For not only does it produce complexity, we're going to see that it produces robustness and novelty. Thank you.